So hello guys, in today's video. Today we'll be testing components. I wanted to make a big video about testing components. So today here we are, we'll be testing inductors, transistors, capacitors, and how to measure them if you don't have RLC or CLR or just a meter that measures them. Of course here I have a multimeter that measures capacitance, and I can measure inductors with a scope, but I will show you how to do the thing. So let's get started with simple measurement, how to measure with a limited current power supply, how to measure or maybe a precise voltage power supply, how to measure resistors. So you don't imagine that you don't have a multimeter that measures it, you just have a power supply with precise ammeter. So here we have 220 ohm resistor, and let's connect it up. We just deliver the power to it just like that, and I will crank up the voltage until we see something that can be used in our calculations. For example, like 2.2 volts can be okay. It's like a maximum, nearly end of the range here. But it's limited in terms of current, so that's what we want to have here. So right now we know that the current is 10 milliamps, and we know that the supply voltage is 2.3 volts. So if we know the formula, the resistance is equal to voltage divided by current. So we just grab our calculator, and our voltage is 2.3, and we divide it up. By our current, which is 10 milliamps. So like that, and we see 230 ohms. Of course I could connect another voltmeter here and measure it this way, but it's precise enough, I think. So let's connect another resistor, again with a current limit. So as you can see, when I disconnected the load, the voltage bumped up. Here we have much higher resistor, so I will set the voltage to be, for example, 6 volts, and we will switch to microamp range on my multimeter, and we have 59.8. So right now we divided up the thing. We divide 6 volts by 59.9 expanded minus 9, and that's what we see, 100k resistor. So that's what we really have here. It's a 100k resistor. So this is one way to measure resistors, test them with real power supply, and this is how voltmeters are really working. So then another component that we can measure is capacitor. In terms of capacitor, we'll be not limiting current, we'll limit the voltage to roughly 10 volts, like that. And right now I want you to focus when I will connect the power, what happens with the needle. So I shouldn't miss the... Okay, so here's the supply voltage, here's the ground. So right now a zoom onto the ammeter on my power supply, and look what happens when I connect the power. The needle bumps up and then goes down. So that's what I wanted to show you. So let's right now discharge the cap. Here's the capacitor. Right now I think it's discharged. And let's connect it again. Boom, the needle bumps up because the current flows through the capacitor in order to charge it, and then when it's charged up, it's good. So we know that it is not shorted or anything, it just charges up, discharges. Pretty nice. It's too low voltage to create sparks, but that's the simplest way to test capacitors on a power supply like that. And when it comes to inductors, and there's no simple way to measure them really with a DC source. But I think that very slightly you can see that on a constant current setting, when you turn it on, you can see that when you're changing the current that flows through, which is pretty low in this case. Let's switch to ammeter. That it overshoots a bit, so it tries to sustain the current. So what we can observe here is that simply that inductors doesn't like the changes in current, and capacitors don't like changes in voltage. Yeah, and that's pretty much the whole principle of this measurement. Another thing that we can test with a DC source like that are LEDs. So we tested inductor, which is not a very successful test, capacitors, very precisely measure resistors, and let's right now grab my bag full of LEDs, and let's grab a single LED from it, like that, and right now on this red wire I have hopefully the plus, and on this one minus. So we connect up the LED, turn on the supply. Okay, so we got the LED, we turn on the power supply, and we start to crank up the current. And we can see that the LED starts to shine somewhere here. It draws very small amount of current, so you can switch to milliamps on my ammeter, and that's what we see, which is 5.8 milliamps at 1.9 volts. So right now we know how much current it draws, so we know the voltage and we know the current, so we can calculate the resistance. So resistance is equal to voltage divided by current. So right now I grab my calculator and I put in 1.9 volts divided by 0.005, like that, and 0.05, 380 ohm resistor with this supply voltage. So that's the resistor that we would need to use to limit the current with this supply voltage. So that's another thing that we can test. Another thing that we can test are diodes. So let me grab a diode like this one. Let me check the wiring. So here we go from here to here. Okay. So right now I connect the LED, the diode, I'm sorry, silicon diode, and right now we can see when I will start to bump up the voltage, that the current is somewhere like nothing on 0.4 volts, on 0.4, 0.5 it's still like nothing, and at 0.6 you can see that there is this threshold and it starts to conduct some current. So we can find the point where it starts to conduct with a normal diode like this one. Then we can grab a Zener diode and test it as well. So I will find the Zener diode. Okay, so here I got a 12 volt Zener diode, pretty thick one. It's a 1 watt one, if I remember correctly. So let's connect it up with the right polarity, so like that. and like right now let's increase the current a bit, and we can see that it limits itself to like 1 volt or something like that. So it starts to conduct somewhere around this voltage because my power supply limits it, and that's the way, and it conducts like 50 milliamps or something like that. So let's right now connect it in reverse. So right now here goes this and this, and right now doesn't conduct, doesn't conduct, doesn't. With a normal diode it wouldn't conduct, but with this diode from some voltage it starts to conduct, as you can see. 1 amp, 1 milliamp, 2 milliamps. I increased the input voltage a bit. So as you can see, it's a Zener because my power supply limits it to 12 volts. Okay, so as you can see, my power supply limits the voltage not to the higher than the 12 volts, to not pass more current. So we can see that it conducts when the 12 volts are here. But how it would look like with a normal diode instead of a Zener? Instead of a Zener, I can increase the voltage, increase it, and even up to 16 volts, and nothing happens. But with a Zener, because of the current limit here, it stops increasing the voltage on 12 volts because of the losses on the transistor and stuff like that. So this is how we can test Zener and the threshold voltage of the Zener when it starts to conduct the reverse bias voltage. So that's the DC side that we'll do. Let's right now put here a scope and a function generator. Okay, so in order to make our signal appear on the scope here, I have set my power supply to 12 volts, then the power is connected to the function generator, and the function generator goes to the amplifier, and then we have the wire from the amplifier here with our triangle wave for measurement. Okay, so after connecting everything up in a very simple schematic, which is just a resistor to measure current, and here I can show you this. We just pass, the resistor is on the other side, so it's on the ground side, but it doesn't change much stuff. So we are measuring the voltage on the resistor and on the element. We have the function generator supplied by my variable bench power supply, then it goes to amplifier, and then it goes through a resistor, and we are measuring voltage drop across a resistor, which is the current, which is the Y channel here, channel 2, and it's yellow. So as you can see, from some voltage it starts to conduct a current, and then it stops and it doesn't pass reverse current through it. So it's in a diode. We are testing diode, and right now in my scope it is on the panel with menus, and you just hit display and then format to XY, and then we can just see the curve. Right now, if I will replace this diode with a Zener, it's a in reverse, and rise the voltage, I need to go to YT mode, and from some voltage I think we'll fry it up. Oh, and right now, ooh, we braked it. You saw the smoke, I think. Okay, so let me grab a new one. I got a few of these, but let's try not so high voltage on it. Okay, so it's polarized the right way around. And here, just a bit of the current flows through it, and we can see the little bump here. As you can see, the reverse voltage. It then conducts in reverse. So it's a Zener diode. Okay, so let's lower down the voltage again. Amplify the channel 1. Let's connect a resistor right now, 220 ohm resistor, pretty noisy there, but as you can see, that's what we see, just a regular curve. So the voltage is proportional to the current. Here the curve will be even smaller, even non-visible. With this one it should be higher. Boom, you can see the curve is much higher because the current flowing through is much higher too. So let's right now connect a capacitor, and right now with capacitor we are at pretty low frequency, and I would say that it conducts pretty high current, 200 milliamps even, or even more, and this is what we are seeing. So we have, and right now it's a good time to explain LCR figures. Don't know how to pronounce it. So here I have nice drawings of those LCR figures. I would call them VI curves. So here we have phase shifts. Pi phase shift, 0 phase shift, pi fourth phase shift, pi divided by 2 phase shift, pi 2, pi fourth, 3 pi 2s phase shifts. And as you can see with this thingy, we can tell that the phase shift is probably minus 45 degree. And we were right. Here we can see the relationships of frequencies, which we'll test in another video. But with this we can tell what's the phase shift of this capacitor, what the phase shift is, what makes the phase shift in our circuit, basically. So by adding capacitance of my body, I'm not changing nothing here, it's too low frequency. But okay, let's test a diode. Hopefully it won't break. Okay, and right now it shines, I think you can see it, and let's go to YT mode, lower something, and it's nearly the same, but it starts to conduct much later than the normal diodes. Let's right now, instead of this, let's lower the voltage a bit again. Let's connect a coil right now. And again, a phase shift. Nearly the same phase shift as with the capacitor, but it's probably in the other side, to the other side phase shift. So that's basically the one setup, how to test components, if they are right, if they are not shorted. So we had the very simple one with a power supply, which was just to tell if something works and what are the voltages. Here we can not only tell the voltages, we can tell the phase shifts, but not values of the components so much. So let's right now tell the values exactly. The resistors can be calculated from here based on the drop that we have of the signal, or the current that is drawn here, because here we have a shunt resistor. So let's right now calculate the values of inductance and capacitance. So we have our function generator in this testing board. Let's check if we have the signal on the output. As you can see, we got it. So what we'll be testing there. So a bit of theory before. So we input our signal, which in our case is a square wave. I will lower the frequency of it a bit. Bit low, so let's increase it like that, and this should be good, more or less. 4 point something kilohertz. The rising edge needs to be accepted right now because I don't have other source. Okay, so we input the signal. It goes through 1k ohm resistor and goes to the capacitor, and this is the module that we'll use to measure capacitance. We will be measuring with our scope voltage across here, and then this is how our input signal looks like. This is how voltage on a capacitor should look like. So we will measure the delay or the time before the voltage is connected to the capacitor, and then when it's charged to 63% of the highest voltage. So we know that the time constant of RC circuit is R times C, so the capacitance will be equal time constant divided by R, and in our case R is 1000 ohms, 1k ohm. Then we pass through a signal through 10 picofarad capacitor, and then we have a parallel resonant circuit here. Here we'll connect our unknown inductor in parallel to 1 nanofarad capacitor, and then we'll measure, we'll see something like that, a bit of an oscillating here, and the capacitance is 1 nanofarad, which is 1 times 10 to the minus 9. And the resonant frequency of a parallel circuit like that is equal to 1 divided by 2 pi square root of L times C. And L will be equal to 1 divided by 2 pi f squared times the capacitance. So let's right now try to measure capacitor. So let's connect this capacitor. I tested this capacitor on this. Okay, so right now the test will be with a bit smaller frequency, and with a bit smaller frequency what we do is the same formula. So the time, which in our case is 460 microseconds, we divide it by our resistor, and which is 1000 ohms, and this is what we got, 460 nanofarads. And this is a bit closer because this one should be 330 nanofarad, but it can be slightly off, so that's how I did it. Let's right now test inductors. So right now into our test device here, I put my probe across here, grab our coil, which is hand-wounded coil. So right now, in order to calculate it, we grab the formula that I showed you, which I have somewhere here. So right now we need to do 2 pi times the frequency, which is 156 kilohertz, just like that, then square it, multiply it by our capacitance, which is 1 nanofarad. So 1 nanofarad is 1 times 10 to the minus 9, like that. And right now invert it, and boom, that's what we got. And this will be pretty big inductance. It will be in millihenry, and it's like 1 millihenry. So we have somewhere around 1 millihenry in this inductor. So this was a pretty long video, a big guide to testing electronic components with your power supply, with oscilloscope, how to see the VI curves of those components, and this is a additional circuit that you can build yourself to test those components. And see you guys in the next video.